Well, good afternoon. I thought I'd tell you a little bit about what's occupying a lot of my time lately, which is trying to characterize, thinking about characterizing cool giant planets in reflected light. And this is all work that our whole group is contributing to. The motivation, this is, by the way, is WFIRST, which is in phase A right now and is slated to launch around 2025. This is the leftover spy satellite that was gifted to NASA by the intelligence agencies and is now being considered, a design is being developed to do exoplanet and dark energy research with it. So this is planet-star flux ratio for dividing the brightness of a planet observed at some band by the brightness of the star. And this is angular separation. So this is the kind of the parameters that people who do direct imaging think about. And so like the HR 8799 planets are these red dots, and they're something like 10,000 times, 20,000 times fainter than their primary star. But with a coronagraph from the ground, adaptive optics, we're able to, the observers are able to blank out the star and see the individual planets. This line, this dashed line, shows the contrast limit for HST, roughly, for imaging young planets. This line here, labeled GPI, is for the Gemini Planet Imager, which is currently doing a search of 600 young stars looking for companions, and found 51 Area B, which we published last year about this time, last August or so. JWST wasn't really designed to be great for doing direct imaging, and its contrast curve is something like this. What we really want to do, though, to see planets in reflected light is we have to look much, much fainter. So it's like something like a part in 10 to the minus 8, or a part in 10 to the 8th, would get you these blue circles, a lot of the known radial velocity planets. So these are planets we know exist, Jupiter mass planets, a couple of AU from their primary star. This is about how bright they would be. And this blue curve shows what WFIRST would be able to achieve with a coronagraph. The X's are a model of new planets that WFIRST might be able to discover that are not yet known to radial velocity. So Neptunes or sub-Neptune sized planets. Of course, ultimately, if you want to get down into the very faintest planets, to see your Earth twins, the ones you want to look for habitability, you have to go even fainter and closer to your star, way down in the bottom left of the figure here, and that would be the domain of the next generation after WFIRST, something like HabEx or LIVOIR, which are missions that are currently being studied. Why do we care? Why do we like looking at planets in reflected light? What about transits? With transits, we're probing the outer, as you well know, the outer reaches of the atmosphere. We're looking at photons that are skimming through the low-density upper atmosphere. And this is often the region that's very highly affected by photochemistry. There could be hazes. It may not tell us what we want to know about the much deeper atmosphere. Whereas if we're looking at reflected light, we're looking at photons that have drilled down, say reflected off a cloud layer, reflected off a surface, and come back through the atmosphere. And often these are photons that have experienced much more of the mass of the atmosphere and can tell us more about the overall bulk state of what we're looking at. This figure on the left is a figure that Caroline made comparing for GJ1214b. If we look at the difference between a baseline case, how big of a signal are we looking at? And the top and bottom panels are presented on the same scale. So if you're doing transit spectroscopy, the difference between just looking at a billiard ball and looking at some particular model for 1214b in this case is you just see these little bitty jiggles. If you're looking at reflected light, the photons have come in and gone out, the signal is much bigger. And so the deviation from a baseline model is much larger. And so it gives you an idea that we're much more able to probe, say, molecular abundances or clouds, or whatever we're interested in the atmosphere. So what science are we interested in? Well, mostly with WFIRST, we're going to be looking at gas giants, ice giants. What can we learn from these planets? Kind of following up in Jonathan's theme, we're looking at the history of planetary science. Here's Jupiter from Pioneer 11. And going even further back, here are spectra from Slipher in 1909 of solar system giant planets. This is a photographic plate where he's taken a spectrum. The top one is the moon. So here's the moon. You're looking at reflected solar lines. But then you look at Jupiter, Saturn, Uranus, Neptune, and you see all these black stripes, which are absorption bands. And in 1909, people did not know what these were. But it turns out they found within about 10 years or so, it became apparent those were methane, and we knew that there was methane in the atmospheres. So in terms of recapitulating the history of planetary science, that's kind of the first level information we're going to get from WFIRST for giant planets, is looking at methane. So here's model spectra, or a model in blue and Jupiter spectrum in red. These absorption bands are methane that you see punctuating the optical. So what is it that controls the shape of the spectrum? Okay, there's methane in the atmosphere. What are we looking at? And one of the most key things in any reflected light spectrum is what's controlling the scattering. In the blue, we have Rayleigh scattering, which is very efficient. Photons come in, scatter, and come out. But at redder wavelengths, the Rayleigh scattering cross-section is smaller. Photons drill deeper into the atmosphere before they scatter, and they're much more likely then to run into unsavory characters like methane, the sodium, potassium, or water, and get absorbed. And so in this case, the photons just don't come back out in the red where they do in the blue. But if we add a cloud layer up at the top of the atmosphere, both the red and the blue can get scattered. So much of understanding reflected light spectra is really tied to understanding the clouds that you have, where the clouds are, what are the properties of those clouds. And here's just a comparison of, say, Uranus and Jupiter, and a model of an atmosphere, giant planet atmosphere with no cloud in black and with a cloud in the dashed line. And you can see how big of a difference it can make at the longer wavelengths. So if we imagine we start out with Jupiter, say sitting out at 5 AU, and we start pushing Jupiter in, its atmosphere is going to heat up, the ammonia clouds are going to evaporate, and if I'm where the sun is, say Jupiter's coming closer to me, the ammonia clouds evaporate, now we have bright water clouds every place, it's still going to look like a very bright white ball. But if we move it even closer, so that the water clouds evaporate, we have a deep Rayleigh scattering atmosphere, it's going to look very different. And so if we imagine looking for a one Jupiter mass object around different types of stars or different distances from their stars, from the known radial velocity population, we can't just say, oh, it's going to look like Jupiter because it's a Jupiter mass. It matters a lot what the temperature of the atmosphere is and what the clouds you have are. And of course, if we take Jupiter, we've got all this methane in the atmosphere, H2S, ammonia, all this stuff. It's in Jupiter safely ensconced below the clouds. Now it's in the atmosphere, it's talking to the ultraviolet light, and you're going to have a lot of photochemistry, and who knows what the spectrum's really going to look like. So Jonathan showed this figure yesterday. I thought I'd throw this in. This is for the most observation for HD 209458b. And if you have, here we looked at 1,000, back in the 90s even, we looked at 1,000 K atmosphere. And this fact that you're right in the blue, dark in the red, just is this case of being absorbed by the molecules, by methane and water at the longer wavelengths. So here's WFIRST. Here's the population of planets that WFIRST will be looking at. This is M sin I increasing on the y-axis, effective temperature increasing to the right. The effective temperature is not just how far the planet is from its star, but also how old the planet is, how long it's had to cool off, because the giant planets cool off as they age. And accounting for all of that, sort of what the estimated range of atmospheric temperature is shown by the error bars. And most of these objects are going to fall in this range where they either are in the water cloud or the ammonia cloud range. A few of them will be so hot they won't have, we predict they won't have any clouds at all. So this is a mock-up of WFIRST at Goddard. And right now we're in the process of defining the spectral bands and what sort of resolution we're going to get from the spectroscopy and the imaging. And this is still all in flux, but this is pasted over albedo spectra from Eric Karkashka of Jupiter, Saturn, Uranus, and Neptune. And again, you see these methane bands, which WFIRST will be measuring. So how do we interpret that? We're going to get spectra of exoplanets The same thing is true ultimately when we get spectra of terrestrial planets or water world planets. How do we interpret, what are we going to see? And one thing that's been very useful in solar system giant planet science is what we call a Baines diagram. It's been popularized by Kevin Baines, who does giant planet science. And this is the two-way optical depth. So for a photon to come into the atmosphere and come back out, how much opacity does it see? The dashed lines are Rayleigh scattering. So if we have we can kind of zoom in here to see it a little bit easier. Here's a blue photon. If it comes in, it Rayleigh scatters and comes out. The black lines are methane opacity. So if you run into a black line before you scatter, you're going to get absorbed. For example, this poor photon here in the orange, it comes down. Before it scatters down here at the dash line, it hits methane opacity, and so it doesn't come back out. Same thing is true, say here at a longer wavelength in the red. But we put in a bright cloud. If we put in a cloud high in the atmosphere, all three bands are going to come down, hit the cloud, and scatter. So we're going to have a much flatter spectrum. The cloud's a little bit deeper. Maybe one of the bands gets absorbed while the other two scatter. And so you can imagine, or even deeper, we're back to the case of the cloudless case. So you can imagine that if you had an actual spectrum, you could start doing forward models, make a bunch of models, try to compare what your predictions are with the actual data. But in actuality, this is a great opportunity to do what Mike just showed you about and do retrieval analysis. So instead of doing 1 million forward models, we can define some cloud properties, say a cloud single scattering albedo or optical depth, a methane abundance, what's the gravity of the atmosphere. Remember, we can't see it, we just see a dot. We're not quite sure how big the planet is. And we can do retrievals to try to work out what we're actually seeing. And so, for example, what if we looked at Jupiter? Signal noise 5, 10, 20, run retrieval analysis. Again, here's our cloud. We can look at where do we have correlations, for example, methane between the atmospheric gravity and the methane abundance. There's a big uncertainty. But we can see how we do. And this is something we're doing now to try to learn what are the issues around interpreting spectra of directly imaged planets. So, for example, one thing, here's one of our examples, retrieving against Jupiter. Here's the single scattering albedo of the deep cloud. And what we find is the retrievals say it has to be bright. We have to have a deep bright cloud. This single scattering albedo of 0.99, which Jupiter has a deep, bright ammonia cloud, so we got that right. The retrievals worked really well for Jupiter. We allow for there to be upper level haze. There's a wide distribution of what it is, but it looks like the models are happy to have some kind of darker haze. Here's single scattering albedo of 0.66, something darker than the cloud, and that's consistent with Jupiter's photochemical methane haze. So we'll say, okay, we like that. But what about the methane abundance, which is what we'd really like to get to? The truth is over here on the left, and the retrieval wants to have a much higher, like a 1% methane abundance, which is too high for Jupiter. So what's up with that? That's not very good. That's not very encouraging. We're going to spend $300 million on a spectrograph, on a chronograph for WFIRST, and we can't even measure methane abundance. What was the issue? And so it turns out that there's this, as I pointed out before, this is the gravity of the atmosphere, the methane abundance. There's a really correlation between the two. If we have a high Jupiter mass, like say it's 25 Jupiter mass planet, it likes to have a high methane abundance. For a lower Jupiter mass, it likes a lower abundance. If we just see a dot, we don't know what the mass is. But fortunately, if we're looking at radial velocity planets, we know what m sin I is. We can measure the inclination by taking images of the system. We can solve for I. We know the mass. From the mass-radius relationship, we could put bounds on the likely size. And so in actuality, we should have a much better handle on the gravity. When we do that, it turns out we put a smaller, tighter bounds on the gravity, assuming we're able to measure the inclination, and we're able to measure the right methane abundance. So these are the kind of problems we're worried about, we're thinking about, trying to derive the requirements for the mission. By the time WFIRST flies, hopefully I'll still be around, but it'll be, it'll be doing these kind of retrievals, and certainly by the time LUVOIR flies in the 2030s, it's not going to be my problem. So there's a lot more to study, though. In the meantime, we may not know the phase we're looking at. There's degeneracies between the size of the planet and the scattering angle you're looking at. Distance from the star, lots of issues that have to be studied and thought about. There's 9 years to launch for WFIRST, but we still have a lot to learn in that time. So I'll stop there. Thank you. Okay.
So with this degeneracy with gravity, you emphasize methane, but wouldn't it affect anything else? Because it's a scale height,
Right, but for these planets are so cold that, and the other thing you would look at in the spectral range is ammonia, which the bands are narrow and they don't really show up, and water, which is out at 0.95, and I didn't point that out. But also for anything, there's that degeneracy. Yeah.
Just wondering why methane.
It's just methane. It turns out the universe gave us something that has lots of strong bands all the way through the optical, and it's sometimes called the giant planet bands because they're just so distinctive in solar system giants. There's a question? Yes? Yeah. Because the reason is, the way I like to think about it, right, is let's say we know the surface pressure at the top of this table is a bar. And what's pushing down is the weight of all the atoms above us. When the gravity is high, every one of these molecules weighs more. And so you don't need as many to get the same pressure at the surface, right? At lower gravity, you need more molecules. And so you can change the gravity, but then you change the number. But then a smaller fraction of them you have more molecules in the column, a smaller fraction have to be methane to get the same effect. And so that's why the surface pressure, gravity, abundance are all tied up with each other. And that's going to be, for the pale blue dot, is going to have exactly these same issues. That's a question for Mike. What statistical algorithm do you use for the retrievals? There's not. Okay. To NASA by the intelligence agencies and is now being considered, a design is being developed to do exoplanet and dark energy research with it. So this is planet-star flux ratio for dividing the brightness of a planet observed at some band by the brightness of the star. And this is angular separation. So this is the kind of the parameters that people who do direct imaging think about. And so like the HR 8799 planets are the -8, or part in 10 to the 8th, would get you these blue circles, a lot of the known radial velocity planets. So these are planets we know exist, Jupiter mass planets, a couple of AU from their primary star. This is about how bright they would be. And this blue curve shows what WFIRST would be able to achieve with a coronagraph. The X's are a model of new planets that WFIRST might be able to discover that are not yet known to radial velocity. So, well, good afternoon. I thought I'd tell you a little bit about what's occupying a lot of my time lately, which is trying to thinking about characterizing cool giant planets in reflected light. And this is all work that our whole group is contributing to. The motivation, this is, by the way, is WFIRST, which is in phase A right now and is slated to launch around 2025. This is the leftover spy satellite that was gifted to Gemini Planet Imager, which is currently doing a search of 600 young stars looking for companions, and found 51 Area B, which we published last year about this time, last August or so. JWST wasn't really designed to be great for doing direct imaging, and its contrast curve is something like this. What we really want to do, though, to see planets in reflected light is we have to look much, much fainter. So it's like something like a part in 10 to the red dots, and they're something like 10,000 times, 20,000 times fainter than their primary star. But with a coronagraph from the ground, adaptive optics, we're able to, the observers are able to blank out the star and see the individual planets. This line, this dashed line, shows the contrast limit for HST, roughly, for imaging young planets. This line here, labeled GPi, is for